Hello everyone, this is Ebenezer Tegaga and I'm your lecturer for power generation, transmission and distribution. And for these lectures, we'll be going to look at power generation, transmission and distribution 1. And this time, which is the beginning of this particular course, we'll be looking at mainly power generation. So first of all, we are going to be looking at the basics of power generation, and then we'll also look at the various power plants that we have. By the close of these lectures, we should be able to tackle almost all the types of power plants that we have for power generation. So to start with, first of all, we'll look at the primary sources of electricity, because electricity, actually the kind of electricity we use does not exist on its own. It's actually the product of a form of energy which has been converted, which means that you have to convert one form of energy into electricity. And the main device or the main machine that helps with that is the generator. But for every generator, you will need a prime mover to drive the alternator. Since we are not actually, our main focus here is to look at how power is generated, we are not actually doing the electrical machines of it. When I'm talking about electrical machines, we are not looking into details how the generator on its own works, where we look at the function of the rotor, the stator and all that. No. For this class, we are assuming that you've already done the basis of how a generator works. All we are going to be focusing on is how we can drive the shaft of the alternator to produce electricity. And like I said, the main component of any generator that helps in generating the electricity and of any power generation plant is the turbine. Every turbine will definitely be coupled to the shaft of the alternator. So once the turbine turns, it in turn turns the shaft of the generator, and then power is generated. So if we have any means by which we can turn the turbine, we will generate electricity. So the primary sources of electricity that we are going to be looking at, we are going to be looking at how these sources of electricity can be used to turn the turbine. So we have some of them, as you can see, listed. All the primary sources of electricity here, we have fossil fuel, hydro, solar, wind, tidal, wave, nuclear, biomass, and geothermal. Before we look at them into detail and how they are used in generating electricity, it is important to note that these primary sources of electricity can be classified as either renewable or non-renewable. If a fuel is classified as renewable, it means that that fuel is capable of replenishing itself, which means that when you use it, a new one is produced to replace the one you've used. And when we consider a primary source of electricity as non-renewable, it means that it cannot replenish itself. Once you use it, new one cannot be produced to replace it. So all the sources of electricity that we have here, like, they can either be renewable or non-renewable. Fossil fuel is usually obtained from prehistoric remains of plants and animals deep in the earth. And so we could have coal as one. We also have oil, and we also have gas. Of course, we can get the gas from the oil. So fossil fuel is one type of primary source of electricity. And since if you use coal is usually mined. Once you mine a particular portion of coal, new one will not be produced to replace what you have mined. Fossil fuel are considered to be non-renewable. But when you look at oil, well, oil is also considered as non-renewable, but if you take a critical look at it, there is a possibility of it being renewable, in the sense that they've discovered that sometimes long after they have abandoned an oil well, I mean they drill oil there for a long time and they abandoned it because they were no more getting oil there, and they leave it for years. Later on, when they go back to the well, they realize that oil is back in the well. So the question is, where did the oil come from? Well, of course, scientists will tell us all about how this oil is produced, but nobody actually has the accurate information as to how all these things work. So most of the time it's all theorized, because if after mining the oil, after drilling the oil and then leaving the well empty for some years, you come back and oil is produced inside, the question is, where is it coming from? Anyway, for a straightforward sake, we will say that fossil fuels are non-renewable. Hydro is water, and water is considered to be renewable because of the water cycle. No matter how you use water, it will come back to you. And then we also have solar. Solar is from the sun. Since the sun's energy, both light and heat, are always constant, they are always there, solar is considered to be renewable. If you use the solar energy to produce electricity, whatever you use, new one will replace it and it's free. The same applies to wind, and the same applies to tidal and wave. Tidal and wave are termed as ocean energy. Since the ocean is always there and it never gets finished, it means that the energy that we obtain from the ocean to generate power can also not diminish. It will always be replenished, so it is renewable. I will skip nuclear and then finish with biomass and geothermal, then I'll come to nuclear, because there's a little controversy concerning nuclear as to whether it's renewable or non-renewable. So biomass is obtained from the remains of plants and animals, or you could say the waste product from animals per se. So for plants, you could use the chaff obtained from the plants, the leaves, or the sawdust from the plants, maybe it's wood or something. And then from animals, usually you use their excreta. So with what will happen is that if there are plants, most of the time plants can be the remains of the plants can be converted directly by burning them. But if it has to do with the excreta from plants, from animals or man, that one you don't burn them. You have to cause them to undergo decomposition to produce gas, and then it's a gas that you burn to generate your power. Okay, so and then geothermal is also there. Geothermal, geo stands for the earth, and then the thermal stands for heat. So when I talk about geothermal, it means that we are producing electricity using the heat from the earth. When we get there, we also look at the since the heat from the earth is usually as a result of the sun's heat bombarding the earth. It means that there will always be heat in the earth. So that is also renewable, just like biomass is also renewable. Now, nuclear. The reason why I said there is a kind of controversy with nuclear energy is that first school of thoughts is that, well, the major and most popular fuel, nuclear fuel that is used is uranium, and uranium is also mined. So the first school of thought is that since uranium is mined just like coal, once you mine and new one doesn't come to replace it, it means that eventually it will get finished. So nuclear energy, that is uranium, is non-renewable. But the other school of thought says that yes, it is true that once you mine the uranium, new one doesn't come to replenish the old one. But if you look at the fuel to energy ratio of the uranium, it's so significant, that it's so high that considering the fact that to get finished may not even be something to consider. or may not be relevant, in the sense that if you take a very small amount of uranium, it can produce large amount of electricity. So based on that, they are saying that, look, and considering the uranium reserve available in the air today, they are saying that there's no way we can ever exhaust the uses of uranium. So under that condition, or considering these facts, it means that nuclear energy is also renewable. Well, so if you are asking the question whether nuclear energy is renewable or not renewable, you can choose either side. All that you have to do is make sure that you back your answer with the necessary points, and you'll be correct. Okay, so let's move on to our next. Okay, so I've already explained what fossil fuel is, and this is a basic diagram showing how electricity is produced from most of the fuel that you have to burn. Example is fossil fuel. So first of all, you burn the fuel and they use the heat from the fuel to heat up water to produce steam. Then the steam is used to drive a steam turbine, which is coupled to a generator to generate power. Pretty straightforward. So this is just a straightforward illustration. Now I'll be looking into detail some of the power generation plants that we have, and to start with, we'll look at a coal-fired power plant. Okay, so as you can see, we have the boiler here, we have the turbine here, we have the generator here, and then we also have the coal supply. We have the coal supply here, and so I'm going to explain how it's actually straightforward, and it's very straightforward. So first of all, the coal is conveyed from the heap of coals that we have here on the conveyor belt into the boiler, and then it is set ablaze, it burns. Okay, then again, we also have a piping system which channels water into the boiler. So what happens is that since there's coal burning in the boiler, when water is pumped into this piping system, when the water gets into the boiler, it's heated up and then converts to steam at high pressure. And the steam comes, steam is water in an expanded form. So anything that expands has higher pressure. So we have the steam coming out from here with high pressure and goes to drive the steam turbine. And then drive the steam turbine, the turbine begins to turn, and because the turbine is coupled to the generator, it turns the rotor of the generator to generate electricity. Now, after the steam turns the turbine, it will lose some of its energy, it will lose velocity, it will lose pressure, and then it will also lose some of the heat. So when that happens, it will come here where we have the condenser. Now, the idea of the condenser here is to convert the steam back into water. And since the steam is water in expanded form, if it can reduce its energy, it will be converted back to water. So in the condenser, water is usually channeled from a reservoir where we have cool water, and the cool water is pumped into the condenser and then goes back. So when the cool water is pumped here, it creates a very cool environment around this area or in the condenser. So when the steam, after driving the turbine, gets here, it loses its heat energy and then is converted back to water, and the water is pumped again into the boiler, is converted to steam. The steam drives the steam turbine to generate power, and the steam is condensed again. The cycle continues. Now the water also that comes from the reservoir to cool the steam, by the time it cools the steam by absorbing heat from the steam. So by the time it gets out from the condenser, it becomes hot or warm and then sent back into the reservoir. It could be a river, and then it's also cooled down again, and then it comes back. The cool water is pumped into the condenser and the cycle continues. So this is basically how electricity is generated using coal. And as you can see, we have a stack here, because once you are burning coal, you expect smoke. And then so the stack here, in the home you call it a chimney, but in the power plant it's called a stack. So the smoke that comes from the burning of the coal is channeled out of the stack into the atmosphere. Okay, so we have some advantages and disadvantages, but we are not going to go through them. I would expect you to read them. We'll be having tutorials to explain some of the things that are in this video or on this lecture notes. So during the tutorial, if you have any questions concerning this, you can ask. I'm saying this because these are all spelled out and they are straightforward. So once you can read, there's no need for us to read them again. But during the tutorial, if you need some of these points to be explained, I would use the time to explain them. But for now, we'll skip all the advantages and disadvantages of the various power plants. The most important thing that we are going to be doing is to describe and explain the mode of operation of the plants. Okay, so this is a typical steam turbine. So you can see that these are very huge turbines. There's a human being standing here so that you can compare the size of the turbine to the size of a human being to know how big it is. And so let's proceed. Next, we will look at the gas turbine system. For the gas turbine system, here we are using gas, which is obtained from crude oil. So the gas is this fuel that we are using in this gas turbine system. So we have two types of gas turbine systems. We have the simple cycle gas turbine system, and then we also have the combined cycle gas turbine system. Now I'll explain the simple one and then also the combined one. Once you understand how the simple one works, the combined one is pretty straightforward. The combined one has a little enhancement to increase its efficiency. But once you understand this, and you know how you also understand how the coal-fired power plant works with all this steam and stuff, you don't have a problem. So first of all, as you can see, we have the combustion chamber here, we have the compressor, we have the generator drive shaft, we also have the turbine here, and we also have the exhaust. So the turbine's shaft is coupled to the generator drive shaft. So once the turbine is turning, it turns the drive shaft and then power is produced. So how does this actually work? It's very, very simple. If you understand how the engine of a car works, this is another simple thing. In the engine of the car, what happens is that fuel and air are all injected into the cylinders of the car, and then the spark plugs create a spark to cause an explosion within the cylinders. Now this explosion produces high pressure waves which actually drive the pistons to cause them to move. So which means that explosion producing high pressure waves cause the pistons to move. A similar technique is used here to cause, this time we are not causing the piston to move, but we are causing the turbine to move. So what happens here is that, first of all, the compressor here actually compresses the air, and then the fuel is also injected into the combustion chamber. So the compressed air and then fuel are all injected in the compression chamber at the same time. So in the compression chamber, we now have a mixture of compressed air and then the gas. Then there's an ignition in the combustion chamber. Once the fuel and air mixture is ignited, it explodes, it burns, and the pressure waves that comes from that explosion causes the turbines to move. So that pressure waves goes to drive the turbine, and since the turbine is coupled to the generator, we have power generated. Now you can see that there's always a common thing to all these power plants. We always have the turbine coupled to a generator. So all that we are interested in is to find a way to turn the turbine, because we know that once we achieve turning the turbine, we know that the end result is that the turbine will also turn the shaft of the generator and power is generated. So going forward, we are mainly going to focus on how we are going to turn the turbine. So with the gas turbine system, the fuel that which is gas is mixed with the air, and the gas air mixture is ignited to cause an explosion, causes the combustion, and this combustion produces very high pressure waves that goes to drive the turbine to generate power, and then the end result of the combustion comes out from the exhaust as smoke, just like the way in the car, once the engine starts, you expect that you should see something from the exhaust. If your engine is good, you may not see it, but you still have some fumes. But when your engine is bad, that's when you see the smoke. Okay, so that's it for this is a simple gas turbine system. Now let's look at what the combined cycle gas turbine system looks like. First of all, before we look at it, understand that the combined cycle gas turbine system has a simple gas turbine system with an additional feature which helps it to become more efficient. So let's look at it. This is a combined cycle gas turbine system, and if you look here, if you look at the top here, you can see we have a gas turbine system, and then if you also look here, we only have a steam turbine a steam turbine coupled to generator 2, where we have the gas turbine here coupled to generator 1. We have a steam turbine here coupled to generator 2. So what is going on here? How does this work? How does the inclusion of this steam turbine here help to improve the efficiency? First of all, like we said, in the simple gas turbine system, we have compressed air which is mixed with the natural gas, which is the fuel, in the combustion chamber, and is set ablaze. So the explosion produces high pressure wave which drives the turbine. The turbine is coupled to a generator to generate power. Then, like we said earlier, the combust, the product of the combustion is expected to go out from the exhaust. But you will realize that if you touch the exhaust of a car, it's very hot. Even the motorcycles, sometimes the exhaust pipe of the motorcycle has bent people's leg when they wanted to get down and their legs touch the exhaust pipe. That tells you that though the exhaust pipe is only channeling the product of the combustion from the engine, it is also very hot. So if the exhaust from the simple gas turbine can be very, very hot, instead of allowing it to just go waste, why don't we use the heat in the exhaust to also boil water to produce steam, so that steam can be used to generate another electricity? So as you can see here in the exhaust, we have another piping system containing water. So the hot exhaust, as it's going out, heats up the water in the pipe, produces steam, and that steam goes to drive a steam turbine which is coupled to another generator, and these two generators are synchronized. At the end of the day, the power from here adds up to the power here, and you have more power. If you remove the steam turbine system from this place, you only have the power generated here. But once you include the steam turbine system, you get additional power, which in turn improves the efficiency of the entire gas turbine system. So this is basically the combined cycle gas turbine system. Of course, everything going on here is just like what happens in the coal-fired power plant. Once the steam comes to drive the steam turbine, it is condensed back to water, and then the water is pumped again, it is converted to steam, and the cycle continues. So here, instead of using a river to produce the cool water that will condense the gas, they are using a cooling tower. Okay, so that is it for the combined cycle gas turbine system. Now we'll move on to the next. Okay, again, the advantages and disadvantages, you read them, and if you have any questions during the tutorials, you can ask. Okay, here we'll look at the hydroelectric power station. or hydroelectric dam. So here the primary source of electricity is water. We are using water to generate electricity. How does this work? First of all, let's look at the diagram. As you can see, we have a reservoir here, we have the intake, we have the penstock, we have the turbine. This is a hydro turbine, and we have the generator, we have the powerhouse, power lines, and then outflow river. It's also called the tail race, but let's focus on the mode of operation. First of all, this is actually the dam. So the dam is created to block the water in order to create a reservoir. So as you can see, this is the dam and this is a reservoir. And if you know the Eureka can experiment, the deeper you go in water, the higher the pressure. So what is done is that there's a tunnel that is created beneath the dam, okay, closer to the bottom of the dam, and that tunnel is what we call the penstock. So in other words, we create an opportunity for a high pressure to be created beneath the water. We want the water to come out from the reservoir at high pressure, and that is the idea of the penstock being beneath the dam. So what happens once the intake is open? We expect that water should rush through the penstock at high pressure to hit the turbine blades to cause the turbine to turn, and this turbine is coupled to a generator which generates electricity. And then after hitting the turbine blades, the water comes out from the overflow river or the tail race, basically. In the next slide, we'll be looking at how the turbine of the we'll be looking at how a hydro turbine looks like, and a few other features that helps its smooth operation. But basically, this is how the hydroelectric dam actually functions. Pretty straightforward. So this is the hydroelectric turbine system. These are the blades, and these structures that you see here are what we call the wicket gates. This is the turbine, a generator shaft, the turbine shaft coupled to the generator, and this is the generator side. The generator has the stator and the rotor. Once the turbine turns, the rotary movement is transmitted to the rotor, and then power is produced. Now, so as you can see, water comes through the wicket gate. In the previous diagram, we did not see the wicket gate. So now this is a closer look at this turbine system. So the water goes through the wicket gates and hits the turbine blades, causing them to turn. Now, what is the function of the wicket gate? Yes, it is true that we need the water at high pressure to drive the turbine blades, but if the pressure is too high, it can break the blades. So you don't just want to direct the water with high pressure to drive the turbine. You want to have some amount of control over the amount of pressure that the blades receive, and that is a function of the wicket gate. So this is what happens when there's too much pressure hitting the turbine blades. The wicket gates close to reduce the pressure, to reduce the amount of water, and thereby reduce the pressure until the pressure is at the level that is required. Then when the pressure is dropping, the wicket gates open to allow more water and more pressure to drive, so by to hit the turbines. So by so doing, we ensure a constant, almost constant amount of pressure to drive the turbine blades. And if you do that, you ensure that the turbine blades are also safe. They don't get broken by high pressure. So basically, this is how the wicket gates also function. And this picture is our almighty Akosombo Dam. So as you can see it here, this is the dam. This is the water lake. So this is the dam, and as you can see, the dam blocks the water lake, the water, and it has created a reservoir. And beneath the dam we have the penstock. So 1, 2, 3, 4, 5, 6. 6 penstocks tells you that we have 6 generators. So here the water goes through the penstock, just like we explained, and it goes to drive the hydro turbines coupled to a generator, generate electricity, and the water comes out from the tail race. This is a tail race, or the outflow river. Now as you can see, there far away here we also have another structure there. This structure is what we call the spillway. It's called the spillway. Yes, it is true that most of the time we are more concerned about having more water in the dam, and it's as if we never get to have enough. But we always have, most of the time we have what we just need to produce our power. But there's also the tendency that there can be so much water in the reservoir here. The inflow of water, if the rate at which the water is entering the water lake is much higher than the amount of water coming out from the penstock, coming out from the dam, it means that eventually the reservoir is going to overflow. And before it may even overflow here, as it rises, it may go into the forest and flood the forest. And if you have some settlements, people settling in those areas, it's going to cause flooding. And since you don't want that to happen, this spillway is there so that in situations where the water level goes beyond normal, there are some gates there that will be open to spill some of the water. So by so doing, you then end up flooding the forest or the villages around. So that's the function of the spillway. Also, we have some advantages and disadvantages. You read through them. If you have any questions during the tutorials, you can answer. You can ask your questions, and I will give you answers. Okay, so the next power plant we are looking at is wave energy. Now, wave energy, like I said, is together with tidal energy. They are all what we call ocean energy. And when we are talking about wave energy, we are talking about the energy that is or can be obtained as a result of the rising and falling nature of the surface of the ocean, or the rise and fall of the ocean. You know, the ocean is not still. It's always, the surface is always rising and falling, especially when it's close to the structure. You can always see it rising and falling, rising and falling. So, and that's what we call the wave. So this rising and falling nature of the sea can actually be used to produce electricity. And this diagram here illustrates how that is done. So first of all, we have a chamber. As you can see, this is a chamber, and then we also have a concrete here. So in this chamber, if there were no ocean here, this chamber will be empty, filled with air. This side is open, this side is also open. So this opening here allows water from the sea to enter the chamber, and then this opening is blocked, and in the path in this opening, the turbine and the generator are installed. So what happens here in the chamber, since the water is expected to be rising and falling, when the water rises in the chamber, it pushes the air that is in the chamber out, and as the air is rushing out, it turns the turbine here, which is coupled to a generator, to produce electricity. Then when the water is dropping, when the level of water is dropping, it sucks air from outside into the chamber, and as the air from the outside goes through the chamber, it continues turning the turbine. And I'm sure some of you may be wondering, okay, if if the water rises and pushes air and tears the turbine, when the water is falling and sucks in air, will it change the direction of the turbine? No. The pitch of the turbine blades are designed in such a way that whether the air is going right or coming left, the turbine blades will continue in the same direction. Will continue in the same direction. So when the water rises and falls, the air is pushed out or sucked in, the turbine will still be turning in the same direction and power will be generated. Okay, so this is another illustration of the wave energy plant. So this is a 3D illustration, but since we've already discussed it, the same principle applies here. Okay, we also have advantages and disadvantages. Next, we look at the tidal power. With the tidal power, we have two types. I will use this one. I will talk about this, and then we'll also talk about this. This is pretty straightforward, but this will require a bit more of explanation, not too much though. Here we have some turbines installed in a water body, and usually this water has to be the kind that flows. So just like a water lake. For the water lake, when you look on the surface, it looks very still, but don't be deceived. If you jump into it, you realize that it's not still at all. Beneath it, the water is flowing. The water is flowing. So here we use the streaming nature of the water to turn the turbine. If it were wind, we can say that when the wind blows against the wind turbine, the turbine blades, it turns the blades, and you can use that to generate electricity. But in this case, we are dealing with the water. The water streams, and it is streaming against the blades, cause the blades to turn, and we are able to produce electricity from that. Then on the left side, we have another type, which makes use of an estuary. Now, as you can see, we have another sort of dam here, and an estuary is created. So what happens? Since the amount of water from the sea is usually more than what can go through here, there's always a high level of water here. Then once you have high level of water, it creates more or less another form of dam. It creates more or less like the scenario that we have in the hydroelectric power plant, just like this. So this is the dam. The water flows through the penstock. Here there's no penstock, but we have the estuary. So a similar scenario plays here. So the water from the sea rises up here because of this dam, and beneath it we have the estuary. So the water with high pressure goes through the estuary, and as going through the estuary, in the estuary we have the turbine and generator installed. So as the water goes through it, it turns the turbine, and then power is produced. Now sometimes the flow of the water could start that by the time it goes down here, the water level on the right side would have risen. Then now instead of the water going this direction, it will change its course and start going through the estuary from right to left. Then when it rises here again, where this is down, the water goes again. So at the end of the day, the water goes through the estuary like seesaw, and whether it goes left or right, the turbine turns the same direction, and then power is generated. Okay. Then also we have another type of ocean energy which is used to produce power. It's called ocean thermal energy conversion, or OTEC for short. Okay, now basically the ocean thermal energy conversion makes use of the temperature difference in the ocean. It makes use of the warm water temperature on the surface and the very cold water temperature beneath the ocean. Now the warm water at the surface of the ocean is usually around 25 degrees Celsius. And then the cold water that can be obtained from beneath the earth can be as cold as 5 degrees Celsius. As cold as 5 degrees Celsius. So how do we use the warm water at the surface of the ocean and the cold water from beneath it to generate power? Simple. Yes, we know 25 degrees Celsius may not be high enough to boil water. So if we cannot use that to generate steam to drive any turbine. But ammonium, for example, has a very low boiling temperature. If you bring ammonia, if you bring ammonia to a temperature of 25 degrees Celsius, it will change to steam instantly. So this time, what we are doing is that we pump ammonia. We pump ammonia or the working fluid, any fluid that has very low boiling temperature. But the most common one used is ammonia, though it also has its own disadvantages in terms of its impact on the environment or even human beings. So now here we have the warm water from the surface of the ocean, and it's pumped here, and as you can see we have a coil. So the water is pumped here and goes through the coil and is expected to go out into the ocean, beneath the ocean. Then also we have the cold water pumped deep down the ocean, also into another coil. These and these are what we call heat exchangers. So it is pumped, the cold water is pumped into this coil to do some work, and it also goes out back into the sea. So what is this hot water doing? What's this cold water doing? As you can see, we also have another piping system which is different from this one and this. This one is on its own, but here it is surrounded by the coil filled with warm water, and here surrounded by the coil filled with cold water, and it is in this pipe that we have our ammonia. So what happens? The ammonia is pumped into this heat exchanger. When the ammonia gets here, because the temperature here is around 25 degrees Celsius, it's converted to steam or vapor ammonia. So the vapor or the steam goes to drive, let me use vapor, the ammonia vapor goes to drive the turbine coupled to a generator to generate electricity. Now the ammonia needs to be converted back into liquid form before you can pump it back here for the cycle to continue. So in order to do that, since ammonia has a low boiling temperature, it means that for you to condense it, you also need an extremely low temperature to condense it, and that's why we have the cold water from the bottom of the ocean coming in. So this cold water comes here and creates that temperature that is necessary to condense the ammonia. So when ammonia gets here, it releases the heat, because the heat is absorbed by this cold water, and once it releases the heat, it's converted back to liquid form, and ammonia is pumped again into this heat exchanger, converted to vapor, drives the turbine, converted to liquid, and then the cycle continues. So at the end of the day, we are using the warm water temperature and the cold water temperature to generate power, using ammonia as a working fluid. Now we are saying ammonia is a working fluid because it absorbs heat from a source and then uses that heat to change its form to do some work. The heat is not doing the work directly, it's doing the work through the ammonia, which is the working fluid in this case. So this is how the OTEC works. There are some benefits of OTEC in the sense that you see this temperature 5 degrees Celsius. This temperature is cool enough for refrigeration and air conditioning. So apart from, if you're able to channel water from deep down the ocean, which is very expensive, if you only focus on use to generate electricity, you may be underutilizing that water. So instead of using it just for electricity, you channel some for air conditioning and refrigeration. And aside that, the water that is pumped from the ocean also contains some minerals and food that you can use to feed fish if you have a fish pond. So it can also serve for the purpose of aquaculture. So these are the other benefits that you can derive from OTEC. Okay, so I already said this. So we move on to the next. The next is solar power. With solar power, here we are producing electricity from solar energy, which means that the energy from the sun is what we are using. And we have two types of energy from the sun, two major types of energy from the sun. We have the heat energy, we also have the light energy. And these forms of energy are what we use in generating electricity. Now, we have what we call the solar photovoltaic, which is or solar PV, which most of us are familiar with. Then we also have what we call the concentrated solar power, the CSP. While the solar PV makes use of the light energy from the sun, CSP makes use of the heat energy from the sun. So we are going to start by looking at the CSP technologies. There's a little write-up there for you guys to read, but I'm going to explain everything that you're going to see in the write-up. So generally for concentrated solar power technologies, like I said, they use the heat energy from the sun. And the way they use the heat energy is that they find ways of concentrating the heat energy, and the way they do that is by using mirrors. These mirrors are designed to concentrate the heat energy from the sun, and then the concentrated heat is used to bombard a piping system which is containing the working fluid. And this time the working fluid could be oil or a molten salt or a mixture of the two. Now, when this oil in the pipe is heated by the concentrated heat, this hot oil now serves as a heat source to go and boil water to generate steam, to drive a steam turbine to produce electricity. Now, the first question you would want to ask is that why do we have to, if we succeed in concentrating the heat energy from the sun by using the mirrors, why don't we directly use the heat to boil water to produce steam, drive a steam turbine to produce electricity? Now, the thing about water is that, yes, we can use the concentrated heat energy from the sun to boil the water, but water has a very poor heat retaining ability, which means that when the heat drops, the steam that was being produced will no more be produced. So at the end of the day, slight fluctuations in the heat energy from the sun may cause the steam that is being produced to also fluctuate, which means that when the heat drops, the steam that is produced will also drop. And once the steam level drops, the turbine cannot be driven again, there will be no electricity. So instead of boiling the water directly by using the concentrated heat, we first of all use the concentrated heat to boil a working fluid, which is oil or molten salt or the mixture of the two. These have the ability to retain heat for a long time. So even if during the day you are able to heat the oil, the working fluid, and night falls where there's no more heat from the sun, this fluid, because it has very high heat retaining ability, it can now serve as the heat source for you to still be producing electricity at night. But there's a better enhancement. If you really want to do that, then most of the time they use salt. So they use the oil during the day, and then maybe when I start explaining, all these things will be clearer. So first of all, let's look at the types of solar concentrated solar power concentrated solar power technologies that we have. We have the first one. We have what we call the parabolic throw. The parabolic throw. The reason why it's called a parabolic throw is that the mirrors that are used to concentrate the heat from the sun, the mirrors are designed in the form of parabola. They are parabolic in nature. So if you look at this diagram here, you can see the mirror, you can see the heat energy from the sun. They hit the mirror and they are all reflected onto this focal point. So if you put your hand here, your hand will fry. So if this is capable of frying somebody's hand, it means that it's capable of heating anything, burning anything that you put here. So at the focal point, we have, if you look here, we have at the focal point, there's a piping system that runs through the focal point of all the mirrors. So in this piping system, you can run your oil. So the oil goes through the piping system and gets heated by the concentrated heat, and then that now goes to boil water, produce steam, drive a steam turbine to produce electricity. So if you look at the diagram here, first of all, you can see this is the where we have the installation of the mirrors, and in the focal point we have the piping system which contains the oil, which is the working fluid. Now, in simple terms, or to make things very simple, I'm going to describe the mode of operation of this one by one. But for the first description, I want you to ignore everything here. Ignore everything here. I will explain the use of this later. So now this is what happens. So we have the mirrors installed here, the piping system containing the oil, and then we also have a steam boiler. We have the steam turbine and then a generator. Okay, so the heat energy from the sun is concentrated onto the pipe, and the oil inside gets heated up, and the hot oil goes straight down into the steam boiler. As you can see, the oil pipe now is coiled within the boiler, and then it goes out back into the field. It's heated and the hot oil goes again. Now what happens in the steam boiler? Here water is pumped here into the steam boiler. So when the water gets into the boiler, because we have hot oil running through the coil here, the water heats up. It's just like using the normal heater that you have in your house. If you put the heater in water, it boils the water. In this case, our heater is not the one we plug electricity, uses electricity. It contains hot oil. So the hot oil in this coil becomes our heater in the steam boiler. So when water gets here, the water is heated and converted to steam. It boils and converted to steam, generates steam, which goes to drive a steam turbine, and then the story continues here. We have power generated, and the steam comes here. It is condensed back to water, and the water comes here, is heated again and continues. So the hot oil, after heating up the water, means that it transfers some of the heat. Heat is transferred from the oil into the water without making direct contact. The heat in the oil, which is in the coil here, is transferred into the water to produce the steam. So by the time the oil goes out from here, it has reduced in temperature, and then it's pumped back into the field where it's heated, becomes hot, and then goes and it continues boiling in the water, producing steam, and the cycle continues. Now, the disadvantage in this straightforward explanation I've given is that once it is night or there's no more heat from the sun, it means that when the oil finishes boiling the water and it comes out and it has lost some of the heat, there will be no more heat to heat it up. It means that by the time it comes here, it will be cooler than before, and it cannot do any work again. And that is where this feature comes in. We have the 2 tanks containing salt. What is the function of this? Now, if you know how the car electronic system works, especially the charging system works, it will help you to understand this. So since you are all electrical electronic students, I will use that to explain and then bring it here. Now, the main power generator in the car is the alternator. Now, and the battery is used to usually start the engine, or when the alternator is not running, you can use it to power your sound system or any electronic in the car. Now, when your car is running, the alternator produces power. That power is sent to your electronic system and you can use it for anything, your lights, your radio, everything. So directly from the alternator you can use the electricity. But while you are using the alternator, the car is running, part of the power that is comes from the alternator to go and drive to go and be used in your car, part of it is channeled to charge the battery. Because anytime you start your car, it uses energy from the battery, and if the battery is not charged, you keep sparking your car. It will get to a point when you spark your car, it won't spark again because there's no more power from the battery. So the battery needs to be charged. So when the car is running and the alternator is producing power, the alternator produces power to be used in the car for anything that you want, anything that needs power in the car. The part of it at the same time is used to charge the battery, so that when you put the engine off and the alternator is no more working and you want to put on your radio, just with the battery will now be the supply of power and the source of power for your car. So that is why even when your engine is not running, you can play a radio, you can do anything. All the electronic gadgets in the car will have power. So when the alternator is running, if you compare it to this diagram, it's as though it's just like when the sun is shining. So when the alternator is running, power is sent to your electronic gadgets and part is used to charge the battery. In this same sense, when the sun is shining and the heat is being used to heat up oil to go and do some work, part of it is channeled here. During the day, part of it is channeled here. And in this place, what happens? As you can see, when the oil comes here, it fills this chamber here. It fills this chamber here. Now, we have 2 tanks, the upper tank, lower tank, and this contains salt. So when the oil comes and fills here continues, salt is pumped from the lower tank through its own coil into the upper tank. And because we have oil at high temperature here, by the time the salt goes through this coil and arrives here, it will become very, 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 very hot. And the salt, as compared to the oil, the salt has much higher heat retaining ability. It can retain heat for a longer time. So during the day when the sun, we have enough heat from the sun to heat the oil to do its work, part of the hot oil is used here to heat up salt and is kept here. So now what happens? During the night or in times when there's no heat from the sun, this part of the circuit and this part is taken out. All these are valves. So if you close this valve and you close this valve, nothing will go here, nothing will come out from here. So now the circulation will be only from here to here, and that's what happens. So during the day when you have used the part of the hot oil, you remember what part goes to help produce the electricity, and a part is also sent here to heat up the salt, and the hot salt is kept in this upper tank. Now during the night when this valve is shut down, because During the night, there's no more heat from this point. So you shut off this section and allow only this section to be in place. And what happens? This time, your hot salt becomes your source of heat. So what happens in the night? You now pump the hot salt from this upper tank through the coil back into the lower tank. And as it's going back, it's very, very hot. And as you can see, this is still the oil cycle. So this motor will, instead of pumping the oil here, because this valve is closed, it will pump the oil here to fill this chamber. And because you have hot salt running from the upper tank to the lower tank, it heats up the oil that will accumulate here. So the hot oil now goes and continues doing its work. You see? So during the day, heat energy from the sun is used to boil water, produce steam, to produce electricity. At the same time, part of it is used to heat up salt, and the hot salt is kept here. But at the night, this side is cut off, and then the hot salt now becomes your source of heat. It is pumped through the coil here, where we have the oil now filling. This oil is heated, becomes hot, and goes and continues doing its work. So even in the night, you can still produce electricity. So that is it for the parabolic trough. We also have another what we call the solar power tower. That is also straightforward. It is a tower with a receiver on top of it. Unlike the parabolic trough, where we have the pipes running through the focal point to take the concentrated heat, here the receiver is what receives the concentrated heat. So beneath the tower, we have mirrors installed, and every of these mirrors here is oriented in such a way that the heat energy from the sun it reflects it onto the receiver on top of the tower. So all of these, there can be hundreds of them, all of them reflecting the heat from the sun onto the receiver. So the receiver now becomes very hot, and we have the piping system running up into the receiver and then coming out. Once it runs up into the receiver, it is heated. So your working fluid, whether it's molten salt or oil, is sent up into the receiver. It is heated, becomes very hot, and then goes to do its work, just like the parabolic trough. But based on the design, the circuit can be in such a way that the piping circuit can be in such a way that you can use it to do superheating and stuff. But that's not really our focus. Our main focus here is how we are able to produce our steam to generate power. So your working fluid is pumped into the tower, into the receiver here. It gets heated. The hot working fluid goes now to boil water, produce steam to drive a steam turbine, and then condense back. The water goes back into here, is converted to steam again, drive a steam turbine, and the conversion of the water to steam is done by this hot working fluid. As you can see, the working fluid comes here, it goes through here, and if the water fills here, the hot working fluid in this pipe boils the water, generates steam, and then drives the steam turbine to produce water. This arrangement here is to further heat the steam. So after the oil comes here, boils the water in this chamber, produce steam. Part of the oil is still can be sent here to superheat the steam to increase its efficiency. And after the oil comes here and it gets here, part of it also can be used here. The superheated steam can come here, and the hot oil again can heat it to drive another turbine. So that's the purpose of the superheating. That's the purpose of the superheating that is in this diagram. So that's also pretty straightforward. Next, we have the Stirling dish or the Stirling engine system. Here, as you can see, it looks like a satellite dish, but it's not a satellite dish. Just design. The design is just like a satellite dish, but it is not a satellite dish. Here we have mirrors all over here, and we have the receiver here. Now all the mirrors here reflect the heat energy from the sun onto the receiver. But in this case, for this receiver, we don't have any piping system running in to come out. No. Well, what we have in the receiver is an engine which is coupled to a generator. So just like the way we have a diesel engine, a diesel generator, the main prime mover there is the diesel engine. So the diesel engine is what drives the shaft of the generator to produce electricity. In this case, we have another type of engine which is coupled to the generator to generate electricity. Now, in this engine, we have hydrogen gas. We have hydrogen gas. Now, what happens is that when the mirrors reflect the heat energy from the sun onto the receiver, the hydrogen gas within the cylinders of the engine expand. They expand in a particular sequence, and this expansion of the hydrogen gas pushes against the pistons within the cylinders of the engine, and by so doing, it creates linear motion of the cylinders. And you could, just like in the car engine, the crankshaft is used to convert the linear motion into rotary motion, and that causes the shaft to turn, to rotate. And once it's rotating and it's coupled to the rotor of the generator, we can generate electricity. So this is also straightforward. Then finally, we have what we call the linear Fresnel reflectors, or the linear Fresnel reflector system. This one is similar to the parabolic throw, just that the mirrors are not parabola in nature. They are linear in nature, and they can be oriented in such a way that wherever they are, they also reflect the heat energy from the sun onto the receiver here. Now with this, as you can see, we have what we call the secondary reflector. The secondary reflector is there to prevent the heat that's reflected, some of them, from escaping. So in case the reflected heat, some of them may not hit the pipe directly and may veer off, they rather hit the secondary reflector and then back onto the pipe to ensure that great amount of heat is harnessed as possible to do the work. And once you have the working fluid heated up, the same story continues, just like the way it was in the case of the parabolic throw. So in summary, you can see this is a parabolic throw, linear Fresnel reflectors. We also have the Stirling dish engine system, and they also have the solar power tower. As you can see, the solar power tower is not a small juke. That is a container there. So this is a very huge structure, and the mirrors too are quite very huge. This requires a lot of investment. And if you look at the parabolic throw too, look at the human being standing by. So these mirrors are not small mirrors, very huge ones, very huge ones. Okay, now our next discussion is going to be on solar PV. Now, like I said earlier, that with CSP, it uses the heat energy from the sun. With solar PV, that uses light energy from the sun. And I'm sure by now we assume that you already have the knowledge of semiconductors. So it makes this discussion very easy, because the solar PV, the solar panels are, if you go into details, they function by the use of solar cells. So we'll look at how a solar cell works, and we have different technologies for the solar photovoltaic, but that's not ours to talk about now. So let's look at the electronics of it. So this is a solar cell in operation. Now, the solar cell is basically a PN junction. And we know that whenever a p-n junction is formed, there's a depletion layer that is created, and this depletion layer contains electron hole pairs. So in this case, we can see this is the depletion layer, which is containing the electron hole pairs. Now this type of semiconductor, this type of p-n junction is said that when light energy or photons are light particles, when light particles bombard the cell, the photons hit or they bombard the electrons, dislodging them from the pairs. Once the electrons are knocked off from their pairs, they become free within the material, and they are ready for conduction. So they aid in conduction. So in this case, once you know the idea of the semiconductor is to be able to manipulate its conductive nature to make it conductive or non-conductive. If it's conducting, it means foil biased. So in this case, when the photons hit the electrons and they are dislodged from the electron hole pairs, they become free within materials. Once they become free, if there is any potential difference, the electrons will flow out from the semiconductor and then cause electric current. So this is basically how the solar cell works. Once you understand the semiconductor junction, p-n junction, this explanation becomes very simple. So let's look at a typical installation, basic installation of a solar PV system. What is on the left is just a general view of it. We have the solar panel. Electricity from the panels go into your DC/AC inverter, so you can get both DC and AC from it to your meter. If you want to use it in a house, you can use it in a house. If you want to sell, you can also sell. So let's look at it in details in this diagram. So first of all, we have the solar module, we have a charge controller, we have the battery, we have the inverter, AC loads and DC loads. When light energy from the sun hits the solar module, hits the cells, dislodge electrons, electricity is produced from the solar module, goes through the charge controller, charges the battery, and it charges the battery, and at the same time some also goes to supply AC loads. But you know, AC loads, the output from the solar module is DC, direct current. So it goes to charge the battery, and if you have any load that needs direct current, you just start from the battery straight to the load. When there's power from the solar module and you are tapping from the battery, you're actually taking directly from the solar module. It is when there's no light energy from the sun and there's no power from the solar module that you'll be taking direct from the battery. So for DC loads, you take directly, but in order to supply AC loads, you need an inverter. The inverter will convert DC to AC, so that your AC loads can also have their power. Now, the battery is there for storage, so that in case there's no more sunlight, the battery now becomes your source of supply to your house. So you can still supply DC loads directly or be converted to AC for AC loads using the inverter. The role of the charge controller is one, to perform trickle or full charge. Trickle charge in the sense that during the day when the light energy from the sun is fluctuating, sometimes when it gets to a level that there's no more output from the solar panel, or the output is not high enough to charge the battery takes over supplying, so the battery level drops. Now if it does not get fully, it doesn't go down fully, the battery doesn't become empty of power, and then the light energy from the sun becomes high again, and there's higher power from the solar module. This time, if in this case the battery level just dropped a little, So the charge controller helps to top it up. So that's what we call the trickle charging. Top it up and become full charge. It becomes fully charged. Now, when maybe you have used the battery overnight, because during the night there will be no power from the solar module. You have used overnight. By day, the battery would have been empty of power. So when the sun comes up, you now have to perform full charge. Whilst you are supplying any load, you perform full charge of the battery. And the charge controller also helps that. Another function of a charge controller is prevent what we call reverse charging. Because the output of the solar module is supposed to usually be higher than the power of the battery in terms of voltage. In order for this module to charge a battery, the voltage should be higher than the voltage of the battery. Now, when it comes to the point where the sunlight is low and therefore the output power of the solar module drops, in other words, the voltage drops to the point that now the battery's voltage is higher than this. If you don't do something about it, there's the tendency of the battery sending current backwards, because usually when you have two power sources in parallel, the one with the higher voltage will usually tend to push current into the one with lower voltage and charge it. So if the voltage here drops and is lower than the battery voltage, the battery will be tempted to push current backwards towards the module, and that is wasted energy, and you don't want that to happen. So the charge controller is there to prevent that reverse charging. The current must move forward, not go backwards. Okay, so that is that for the solar PV. Now a solar cell, several solar cells, you put several solar cells together, you form a solar module, and you put several modules together to form a solar array. Okay, now we will be looking at wind power, producing electricity from wind energy. Yes, of course, the prime mover there, the main component that helps to extract the energy from the wind is the wind turbine. And we have two types. We have the horizontal axis wind turbine and the vertical axis wind turbine. And between these two, the horizontal axis is the most common. So every discussion we do will be based on the horizontal axis wind turbine system. So this is a wind turbine. We have the hub, the pointed nose, that's the hub. We have the blades, these three blades. Then we also have the tower. The head of the turbine actually sits on the tower. Then if you look inside, we can see our generator. This is the shaft of the generator. This is the shaft of the turbine. And the coupling this time is done through these gears. We have this gear, and you also have another gear here. So this is a low speed shaft and this is a high speed shaft. I'll explain why we have this arrangement, why we need this particular arrangement. Then we also have some arrangements here, gear arrangements here. Then we have a controller here, we have an anemometer, and we have a wind vane. The anemometer is used to measure wind speed, while the wind vane is used to measure wind direction. So we have yaw drive, your motor, we have pitch. So let's put all these things together to tell something about the wind turbine. So first of all, these are the turbine blades. As you can see, we also have what we call a pitch. For turbines, you can either have a fixed pitch or a variable pitch. The pitch, when I talk about a pitch, a pitch is talking about the angle at which the blade is mounted on the hub. So if it's a fixed pitch, it means that the blades are mounted at a fixed angle, cannot be changed. But if it's variable speed, it means that the pitch, the angle at which the turbine blades are mounted on the hubs can be changed. And it is necessary for you to be able to change the pitch for something I'll be telling you later. Now, okay, let me just go straight forward and say it. What's the essence of having a pitch? To be able to pitch, control the pitch and have a variable pitch of the blades. Now, if the blades were fixed, when the wind is blowing against the turbine, there's a tendency that the winds can break the blades, because it is usually the surface area of the blades that are exposed to the wind that helps the extraction of the energy from the wind. When the wind hits against the blades, it causes them to turn. Now, when the area of the surface area of the blade that's exposed to the wind is bigger, the impact of the wind is higher. So assume you have a fixed pitch, the blades here are fixed pitched. It means that you don't have any way of changing the angle. So if the wind is blowing against the blades and the area surface of the blade facing the wind is high, the wind could blow so strong against that it can break it. And since you don't want that to happen, you will need to find a way of reducing that surface area so that the impact of the wind on the blade will also reduce. So if the angle is such that the area facing the wind is big and the wind is so strong, which is determined, the speed is determined by the anemometer, the controller takes the signal from the anemometer and then uses to control the pitch, controlling the pitch to reduce the area surface. So assuming this blade, as you can see, it is tilted at this angle and the wind is blowing strong against it, you can tilt it in such a way that it will reduce the surface area, and once the surface area is reduced, the impact of the wind will also reduce, and by so doing it will not break the blade. It's just like you, a human being, standing facing the wind directly. When the wind blows, it can push you backwards, but when you stand sideways against the wind, the impact on the wind will reduce. So that's just a similar technique that is used here. But of course, there are times that the wind speed may not be that high. So then again, you control the pitch and make sure that you expose more of the surface area to the wind to be able to extract more energy from the wind. Aside that, we also have what we call the yaw. The yaw. While the pitch has to do with the angle at which the blade is mounted on her, the yaw has to do with the movement of the whole head of the turbine. I'm sure all of us have used standing fan before. There's something you can press at the top of it and it causes the fan, the head, to be turning from left to right. The turning from left to right is what we call the yaw. And wind turbines also have that ability. The reason why it is necessary to have that ability is because the wind direction is not always constant. The wind can change direction. And since the main purpose of the wind turbine is to extract energy from the wind, you want to make sure that the wind is always, the turbine is always facing the wind. So the wind vane is what helps to detect the direction of the wind, sends a signal to the controller, and the controller controls the yaw in such a way that the turbine head will be moved to face the direction of the wind, so that you are sure that at every point in time, wherever the wind's direction is, you have your turbine facing it to do the work. Now, to this shaft gear arrangement here, I said earlier on that we have, this is the low speed shaft, this is the low speed shaft connected to this bigger gear. We also have the high speed shaft connected to this low speed gear. The purpose of this arrangement is to increase the speed of rotation, to make sure that we have enough speed of rotation to drive the generator, because there's a particular RPM that's required to be able to generate the power that you need from the generator. And sometimes when the wind is turning, the turbine is turning, the speed of rotation may not be high enough to drive the generator to get that amount of power we need. So this gear arrangement here is there to help us achieve that. So as you can see, the low speed shaft has a bigger gear, and then the high speed shaft has a lower gear. So what it means that by the time this gear makes one complete rotation, this would have made about 4 times, would have rotated about 4 times already. So this will be turning very slow, but this will be turning very, very fast, very, very fast. So by this gear arrangement, we are able to increase the speed of rotation of the shaft of the generator to generate power. Okay. Okay, there are other terms, yaw, and then pitch. We've spoken about yaw and pitch, but with the wind turbines, they don't roll because they are mounted on a tower. The rolling, if you look at this airplane, for example, rolling is either going this way or that way, going this or that way. But if this aeroplane were mounted on a tower, there's no way it can swing this way or that way. No. So there's no rolling wind turbine. We only have the yaw and the pitch. As the yaw, you can see the face can turn here and there, and then the pitch has to do with the angle of, as you can see, this is a pitch. The blade helps with the pitch. Okay, there is some analysis that we need to do as far as the wind turbine is concerned. It is called the aerodynamics of the wind turbine. Now, this requires some mathematical and fluid mechanic analysis. For the sake of proper explanation, since this requires mathematical expressions and explanations, and they may be the need to write certain things, I am going to skip this for now and proceed with explaining the other power plants that we have. When we are done with that, we are going to have a special recording to explain the aerodynamics of the wind turbine, where we can be able to do the mathematical analysis as well. And I'm sure during the tutorial we'll also go through this. So even if you don't get a video, I'm sure we'll do everything from scratch during the tutorial, but there is high probability that that video will be done, so that in the comfort of your home you can go through them. And the beautiful thing about the video is that you can always go back to where you did not really get, and then listen over and over again until you grab it. So we are going to move on to look at the other power plants that we have, and then later on we'll come back to the aerodynamics of the wind turbine. So the next power plant we are going to be looking at is nuclear power. So in this case, we are converting nuclear energy into electrical energy or electricity. So let's take a look at a nuclear power plant. This is one diagram of a nuclear power plant. There is also another one. Some of these diagrams are actually animated, but because I'm presenting them in full screen, it looks as though you may not see the animation. But I am choosing this to explain because it looks much simpler, and in order for you not to get so much confused, most of the things that are labeled here, you don't actually need them. So in order to make the explanation simpler, we'll use this diagram. Okay, so here we have the nuclear reactor. Inside the nuclear reactor, we have the reactor vessels, and then we also have the steam generator, we have the pressurizer, and the control rods. Now, as you can see, the same water cycle is here again. So all that we are trying to do is, how do we boil this water to produce steam, to drive a steam turbine, to generate electricity? So this water cycle is there. How do we produce heat from the reactor vessel, from this pipe, to boil up the water here to produce our steam? It is through what we call the nuclear reaction. Nuclear reaction. We have two forms of nuclear reaction, and all these forms of reactions produce heat. We have what we call the fission reaction. We also have the fusion reaction. Fission reaction is when one big atom is split into smaller atoms. Then the fusion reaction occurs when smaller atoms combine to form a bigger atom. All these processes produce heat, and these reactions take place in the reactor vessel to produce the heat, and the heat is channeled into the steam generator, boils water, produce steam, drives steam turbine, coupled to a generator to produce electricity. The steam is condensed again, just like in most of the power plants that we have looked at. Now here the focus is to produce electricity, and the heat that we are producing here has to be controlled. Now, if there's no means of controlling the heat that is produced, there's going to be explosion, and that's how nuclear bombs are actually produced, because the reaction that takes place here that produces the heat is what we call a chain reaction. From one reaction to a bigger reaction to a bigger reaction, another one, it continues like that, multiples of the previous reaction. So if you don't control it, there's going to be an explosion. So we have the control rods here to perform that function of controlling the reaction, and by so doing control the amount of heat that is produced to produce our electricity. Now here we can talk about the two types of reactions. You can see we have a uranium atom here, which is split into two atoms, and then we also have helium, we have deuterium and tritium, which come together to form helium. So here we have an atom splitting into smaller ones, and we also have smaller atoms coming together to form a bigger one. So this one is what we call the fission reaction, and this is what we call the fusion reaction. Now, in order to understand the chain reaction, I will use the fission reaction to explain. Here, this is a neutron, and this is the uranium atom. Now, a neutron particle is shot to bombard the uranium atom. When it hits it, the atom breaks into two. For this illustration, it breaks into two smaller atoms. Now, the breakage of the uranium atom into these two causes the release of other neutrons. So one neutron hits this atom, breaks it into two, and releases other three neutrons. Now, each of these neutrons will go and perform the function of this. So this will go and hit another atom to break it into smaller ones. This also go and hit another atom to break it into smaller ones. This will hit another atom to break it into smaller ones. So this is the first stage. This first stage produces three neutrons, which will go and perform the same function as this. So at the end of the day, we are going to have this breaking an atom into two smaller ones. This is doing the same thing. So on the second stage, we are going to have about 6 smaller atoms, and out of these 6 smaller atoms, each of them will produce three. Each of these breakage will produce 3 neutrons. So we are going to have 1, 2, 3, 4. And that will make it 1, 2, 3. That's going to have 9 more neutrons released. And these 9 neutrons that have been released, each of them is going to perform the same function of further breaking atoms, and the reaction continues like that. And each of these breakage produces heat. So here we have one atom broken into 2. Heat is produced. These go and break 3 atoms. Each of them produces 2. Now we have 6. So now we have 1, 2, 3 times the heat that was produced here. And this one in turn go to produce more. So another day we start with one reaction to bigger reaction, and if it's not controlled, there's going to be serious explosion. But like I said, we have the control rods within the reactor. What the control rods do is that they absorb excess neutrons from the reaction. By so doing, they make sure that the reaction is controlled. Once the reaction is controlled, the amount of heat that is produced is also controlled, and it will be safe enough to generate electricity. Okay, so next we'll look at geothermal. Like I said earlier on, geo stands for the earth, thermal stands for heat. So in this case, we are talking about producing electricity using the heat energy from the earth. Now, in order to do this, we have to channel the pipe into the earth and then bring it out. So when water is pumped into the pipe that goes into the earth, because we have heat, a high temperature in the earth, the water that goes into the earth is heated. It is heated and then comes out as steam, goes to drive a steam turbine to produce electricity. Very simple. There's another illustration here. So we have down here, we have the injection well, which sends the pipe down into the earth, and the production well pipe comes out. Hot water comes out with steam, which goes to drive the steam turbine to produce electricity. Now, the hot water that goes after producing steam continues, loses some of the heat, and then can go back into the earth, heated again, the cycle continues. But of course, some of the hot water that comes after being used to generate electricity after the steam is produced from it, part of it can also be sent for direct use. Direct use means if you want to use it to bath, you need hot water or warm water to bath, you can use that. And then some is also sent back into the earth to start the process again. That is that for geothermal. Then finally, we'll look at biomass. We are producing electricity from the remains of plants and the byproducts from humans and animals. You can use human excreta or cow dung to produce electricity, or you can use the fiber from plants to produce electricity. So how do we do that? We have two types of biomass power plants. We have the ones that use direct combustion, and we also have the one that uses indirect combustion. What is the difference between these two? Now, with the direct combustion, the biomass is sent into the combustion chamber and it is burnt directly. So if it is fiber or sawdust, you take the sawdust into the combustion chamber and you burn it, just like the way the coal was sent into the boiler and it's burnt. Here we send the biomass directly into the combustion chamber and fire is set to it. It is set ablaze, it burns, and the heat is used to boil water to produce steam, to drive a steam turbine to generate power. Now, for the indirect combustion system, the fuel or the biomass is not burnt directly. In this case, the fuel is made to undergo decomposition, and the decomposition process produces gas. And that gas that is produced from that decomposition is what you now burn. It's what you now send to the combustion chamber to be burnt. And you can use it directly to drive a gas turbine, or you can use the boil water to generate steam, to drive a steam turbine to generate electricity. So as you can see, the difference here is that with the direct combustion, the biomass is sent directly into the combustion chamber and is burnt. The heat is used to generate water, to generate steam, to drive a steam turbine to generate electricity. But here, the fuel, the biomass is not sent directly to the combustion chamber. First, it is made to undergo decomposition. The decomposition process produces gas, and it's the gas that is sent to the combustion chamber and is burnt. And the combustion can be used to drive a gas turbine directly, or it can be used first to heat water, produce steam, drive a steam turbine to produce your electricity. Now, this is an example of a biomass system. This is what we call the fixed dome biomass system. And this type is the indirect combustion type. So, as you can see, we have the mixing tank here. We have the inlet chamber, we have the digester, we have the outlet chamber, we we have the overflow tank, we also have the gas control valve. Okay, so what happens in the mixing tank? Water is mixed with the biomass, let's say cow dung, and then it is sent down here into the digester. Now when it's sent here, it is left in the digester and it begins to decompose. Now the decomposition process produces gas, and the gas is accumulated up here. Now if this valve is closed and the decomposition continues, more gas will be produced, and as the gas is producing, pressure begins to build up. Now when the pressure becomes high and the valve is still closed, the gas will now begin to push down against the mixture that is here. So that's why we have the outlet chamber. So it pushes down it, and then the mixer cannot come here. And if the pressure keeps building and the gas is not let out, it keeps pushing the mixture here until it comes into the overflow tank. And this here is for you to observe to know that no, the pressure here is too much. Once you see the mixture coming out here, it means that so much gas is accumulated here and some needs to be released. So in this case, the gas that is accumulated here is now channeled through this piping system, and then it can be used to cook. Just like the way you use your LPG gas to cook, this gas also is inflammable, so you can use to cook. If you can use to cook, it means you can use to boil water to produce steam, drive a steam turbine to generate electricity. So this is a type of an indirect combustion type of biomass. Then here we have the direct combustion type. As you can see, we have the biomass, wood chips or sawdust. Yeah, we have the wood chip or sawdust, and then that is channeled straight into the boiler. It is bent, and the heat boils the water in the piping systems here. The water goes into steam. The steam goes to drive a steam turbine to generate electricity. So here, this biomass, the wood chips, are not kept anywhere to digest or decompose. No, they are sent straight into the flames here. They are bent, and the heat is used to boil the water in the pipe here, produce steam, drive a steam turbine to produce electricity. So that brings us to the end of these lectures, mainly talking about the various power plants and how they work. So like I said, I'm going to do a special video on the aerodynamics of the wind turbine, and then during the tutorials too, we would go over them again. Thank you very much for your time, and I wish you guys all the best.